Thank you, Ronnie. So the topic of this webinar is the inversion and rock properties, or more exactly the OpendTect tool you have to achieve an inversion and rock properties analysis in any condition. Okay. So you have different packages available in OpendTect. The geology sequence stratigraphy and 3D geophysics package, attribute and filter, inversion and rock properties, velocities and PSDM. So I will focus on the third one, inversion and rock properties, and all these packages are available to buy or have all the detail about that on our website. So this package contains OpendTect and the following plugins. So I will focus on the one listed in white. The others are subject of other webinars that again you will find on our website. So these different attributes and plugins, they have different objectives and different application. So if you want to do seismic filtering and data enhancement, you will use deep stream median filter and seismic spectral blowing, for example. So deep stream median filter will be used to denoise the data, while seismic spectral blowing will be used to improve the quality. In a further analysis for reservoir characterization, then you will use color inversion. You have color inversion, deterministic inversion, and stochastic inversion, as well as neural network. That will help you to map your reservoir, but also to do hydrocarbon mapping and to achieve your reservoir characterization. So I will first start with presenting seismic spectral blowing. The seismic spectral blowing is an ArcGIS plugin. It's used to increase the resolution of the seismic, and it keeps the noise level to an acceptable level. So it's based on the comparison between the spectrum from the well and from the seismic. From that you design an operator that you apply directly to the seismic using convolution. And I'm going to show you how it looks on OpendTect. So you access to this plugin through the attribute set engine. So in the ArcGIS subselection. So when you click on Analyze and Create, you have this window that pop up. You select the seismic, the well data, so the impedance logs, or that you have computed in your wells, and then you are able to design your operator. So as I say, it's based on comparison between the spectrum from the seismic. So you use the mean spectrum from the seismic from the wells. And then you're able to design the operator. Here is the operator by comparing the the spectrum from the seismic and from the well. So the spectrum from the seismic here is in red, and the one from the well is in green, and the operator is here displayed in blue. So once you define your operator, you apply this to the seismic. So here is after applying spectral blowing. This is the initial seismic after deep stream median filter. So you can see that your reflectors are better defined, they're sharper, and you have some that appear that they were not there before. Also, the end of the reflector is better defined, like here, for example, if you look, or here. So that will help you for the interpretation, and then once you do the better interpretation, you can achieve a better analysis. So once you've done the interpretation, you can go further in the analysis. So you may want to do inversion. Inversion is a process that estimates the acoustic impedance in the seismic data. It is band limited. The input data is band limited, so you have to remember that it's a non-unique process. So there is a large number of models that will match the measure and the constraint that you will give. So different algorithms have been developed, and I'm going to show you the 3 ones that are available in OpendTect. So here's a bit of background. The acoustic impedance is given by the multiplication of the velocity and density. So you can compute that very easily in the wells using the seismic reflection is defined as the impedance contrast. And the seismic trace is defined as the convolution of the reflectivity series with the wavelet. And of course you have to add a little bit of noise because we are in a real environment. So the inversion, any inversion starts the same way. You have to prepare your log, so you have to compute impedance log. For that you need a velocity or sonic log and density. The density you can create one using, if you don't have one, you can create one using the velocity log, but of course it's better to have one that's been acquired in the well. And then you have to tie the well. It is very important as you are going to compare the well data with the seismic data, so it has to be done very carefully. So at this stage you can achieve colored inversion. The colored inversion is based on the empirical study that revealed that the unconstrained path by inversion can be approximately modeled as a convolutional process with an operator whose amplitude spectrum maps the mean seismic spectrum to the mean Earth acoustic impedance spectrum, so from the well, and has a phase of -90 degrees. So how you create create this operator is very similar to the way you create the one for the spectral brewing. It is also an AxiLS plugin. The advantage of the color inversion is it's very quick, and you don't need special skills to do that. And in addition, you don't need to extract a wavelet, and it's not model dependent, so it's robust. And so again, it's very quick, so it's very efficient. It is used for qualitative analysis, and it could be used to determine the interval, the reservoir interval. It also gives a better, it helps also for the interpretation of the horizons. So you also have model-driven inversion. These are AxiLS Earthworks plugins called MPSI plugins. Deterministic inversion is based on the comparison between synthetic seismic and the real seismic. And the stochastic inversion goes after the deterministic inversion. It's assumed they take into account that there is uncertainty on the results. And the average of all the non-unique stochastic realization is the deterministic inversion. To achieve all these two model-driven inversion, you need to estimate a wavelet. You can extract it directly from the seismic. You can also create one, but of course it's better to do that, to extract from the seismic directly at the target, at the depth of interest. So once you've done this wavelet extraction, you can create your model. For that you need horizons that will give the structural constraints, and well data, so the impedance logs that you computed before. This well data will be extrapolated in the zones that you define. Here zone 1 and there is 2 zones, zone 1 and zone 2, defined between horizons or your top and your base. And they will be extrapolated using geostatistic, using kriging. You can compute variogram in OpendTect in the 3 version, 4.3 version. For that, the variogram will give you the spatial coherency and of the and your volume. and you have two variogram, vertical and horizontal. The horizontal can be computed from gridded attributes on horizon. So you just click on variogram. Here you have the different parameters, the range, the step, and the maximum number of pair of leg. So here you just put 3000, press OK. And then you just need to adapt your range and your cell, and then you have your information. You can get the vertical variogram from the crossplot, the well versus attribute crossplot. And then you select a well, and you select an attribute, a log. And here you can, here, compute variogram for column, so you will get again, it's the same principle as for the horizontal one. So with this information, you're able to give better constraint to your model and to have an accurate model at the end. So that was how you extrapolate the well data, but you have also to take into account the horizon that will also give the structural constraints. You have two workflows to achieve the model. You can use few horizons, or you can use the horizon cube. The horizon cube has a very dense number of horizons, so the more horizons, the better constraints will be your model. So that will give a more accurate model. So here's an example. So in red you have the two horizons that have been in green, the one have been extracted from the horizon cube. So you can see there's quite a lot. This is 21 actually. So here is the initial model with using only two horizons, so the top and base, the red one. So you can see here and here, it's not following the seismic. But here, as we had more horizons, it's following. So the model is better. And that will have a big impact on the inversion results. So using the model, you can achieve the deterministic inversion. As I said, it's based on the comparison between synthetic data and real seismic data. And the objective is to minimize the difference between the two. The advantages are that it's a robust method, and it gives a good model with a good model, it will give reliable results, and it could be used to map lithology and saturation variation. The limitations are that as it's model dependent, if the model goes wrong, then the final inversion will be wrong, or won't be as good as expected. Another thing is that it will tend to underestimate the impedance value, so it cannot be used as a model, as it won't give the right value and accurate, so it will give not an accurate constraint. So here are the result of the inversion, deterministic inversion. So that was with the first model, so the one with only two horizons. So that will show you how important is the model. So here you see that it doesn't follow the seismic again, as the model was not following. And here it follows nicely. So that shows how important is the model. But there is uncertainty, and this uncertainty is taken into account by the stochastic inversion. The stochastic inversion will not give one result, but a number of realizations that will meet different requirements. So you will match the measured data in the well, the histogram of the data, and also the spatial correlation function that you've designed, that you've determined using the variograms. The concept of the stochastic inversion is explained here. It is not, actually we do not extract a trace, but we look at this in the frequency domain, but it's much more understandable this way. So first well, here in red you have the wells, and you want to know in the data. So using kriging, you can extrapolate the mean and the variance of the low data as this location, and then you generate as many equivalent impedance realization. Then you get synthetic that you will compare to the real seismic, and the one with the best match is selected, and you repeat the process. You repeat the process. So now I'm going to show you how it looks in, well, how it looks in OpendTect. So here you have the in the attribute engine, you have the stochastic inversion available in the AxialX earthwork subselection. So here I'm going to display the different realizations. So here I computed for 5. So you see that this may vary quite a lot. So there is uncertainty, and all this realization, they match the well data, and they match the histogram of the data and the special the valiogram of your data. So now I'm going to using the stochastic inversion, you can go further, and you can create and determine bodies of properties, and you have information about the connectivity using cutoff, like impedance cutoff. Here, if you select impedance of interest, the range of interest, and then you can determine bodies. So now I can show you the different color inversion, the different inversion results. So it's for the same interval. So this is what you will get if you realize a colored inversion. This is what you will get if you process deterministic inversion, and this is what you get if you do stochastic inversion, so a different number of realization. So once you've done the inversion, you have information about the impedance in your entire volume, and you can go further in your analysis, and you can determine other properties. For that, you can use neural network, which combines different attributes into a meta-attribute, and they will allow you to define objects, to map seismic fasces, and also to do rock properties prediction. For the object and fasces mapping, you have two kinds of neural network. You have the supervised and unsupervised. The supervised don't have any information. You just define different classes, for which defined as a set of by different values of attributes, and you let the distinction between the different classes to do it by itself. For the supervised one, you have information and you give that to the neural network, so you can get you can take into account this information. For the rock properties prediction, you use a different kind of neural network. So here you go into analysis, neural network. And here it's a pattern recognition for the and the object detection. And here the property prediction, so that will use the well data. So here you have a list of attributes. These attributes are just the seismic at a horizon of interest, but shifted that you can, yeah. And then here you select your output. So here, for example, the porosity, and here the wells you want to use. So here you select the interval of interest, and then you press OK, and then you run the neural network. I'm not going to do that, but I have the results. So here is based on the inversion results that we had, deterministic one. So this is the deterministic inversion result, and this is the porosity prediction. So real seismic, inversion, neural network. So that's very easy to do, and it gives accurate result if you had a good attribute selection and you had a good inversion results. So you have all these tools available in this package, but you will not use them for the same way, and you will not use them in any other condition. The objective is for you to achieve this rock properties analysis and description in any situation. So you have two questions. First question you have to ask is about your data quality. If you have a medium pool seismic, you have to improve the quality. So you will do seismic spectral bluing, distal median filter, or if it's really bad, then you will think about reprocessing. So then you will get a good or acceptable seismic quality, and then you will look at the geology. So first you will look if your target is thick or thin. If it's thick, it had one layer, so it's easy. You can apply any kind of inversion you want. The model is likely to be good and to be better and more trustable. So you can do deterministic inversion, and also color inversion is good. If you have multi-layers, then it's like if you had a thin or thin layer, then you will more use color inversion and stochastic inversion because you have to take it back. Another thing you have to look at is the variations. If you have large lateral variations, that will have an impact on the model. If you have quick variation, then the model won't be able to follow, so it's better, more trustable to do color inversion. If it's low frequency variations, then you have to have a good constraint. You have to know what is happening, so you need many wells, and it's better to use horizon cube as constraint of the model. So this is important to know, because then you will be able to define a workflow, and you will be able to know what to do and to save time and be more efficient. So, well, that will conclude this webinar. Thank you for your attention. And if you have any question, I will be happy to answer. And Arno and Christopher's also. Thank you.
Well, thank you very much, Claire. That was a very nice presentation. We've actually had a lot of questions coming through the questions pane. Several of them were answered to the entire audience, so if you're not sure where to find that, look in your little shorthand window up on, it should probably be on the right-hand corner of your window that will show you where you can raise your hand and everything. And then you'll see the answers that were replied to the entire audience. Now, unfortunately, we did have a little bit of audio problem this time, though I think everybody, I think everybody was able to understand the context thoroughly, though, because nobody mentioned it. But in a few places, we did lose the audio at some point. So if you do have questions, please at this time type your questions into that questions pane that I was mentioning. So you can type your questions into the questions pane, or you can raise your hand, the little hand icon with the green arrow, and we'll be very happy to unmute you in the order that you've raised your hand. Now, Arnaud, I know that you are answering questions for several of the people throughout this webinar, so if you would like to address any of those questions, Arnaud and Christopher, you're both unmuted at this time. And actually, if you can hold on to that, we do have somebody raising their hand. So we'll go ahead and unmute you. I'm sorry if I mispronounced your name, Pratibha.
Yeah, hi. It's a really good presentation.
Thank you.
I have one query regarding like depth, pre-stack depth migration. I asked. It is a little bit off the track, but I wanted to raise this question because with the PSDM data, can we go further for things like inversion or attribute analysis? How much we confidently we can produce our data to the, to how much confidence we can go ahead with the PSDM data?
So this is Arnaud speaking.
Okay.
We have done quite some work right now on time-converted pre-stack depth migrated data, and we can say now that we have a bit more experience with it, that if the processing has been done carefully, and that's especially by trying to preserve the amplitudes as much as possible. In that case, you can really do these inversions just like if you would invert a time-migrated data. Nevertheless, what you always have to assess before you're making any inversion, and that is regardless of the migration being done in a time domain or in the depth domain, to decide the volume and see if you have any sort of match at target level between the synthetic waveform you can extract from your well logs and the actual waveform in the processed seismic volume. And if you have a decent match, which is rather fuzzy to quantify, then you can go for the inversion. Some would, of course, the better is always the higher is always the better. You can have a correlation between the two of 90%, 80%, 70%, down to 0, and but at least you have to assess the degree of correlation before you go for an inversion.
Okay, one more question. Like while tying well information to the seismic, we usually take the VSP data or checkshot data. For that, checkshot data is basically it's a vertical component which has been recorded, not three component data, and the seismic is never recorded horizontally. Either it is horizontal or the other dimension. So to work on these discrepancy, how much input, other inputs we can contribute so that that matching should be perfect. Because it can never match 100%, right?
No,
so,
it will never match 100%. What is very important to have the one piece of information you need for tying a well correctly is a good checkshot data of VSP survey. If you have a decent VSP survey acquired with a good sampling rate that is small enough, and that is 20, 30, 40 meters, then you can be very confident in your capability of actually tying the well to the seismic. And that is in terms of localization. That will not say that you have a good match between the well, but at least your data is meant to be placed in the 3D space.
Okay. One thing more, while doing PSDM migration, that velocity information can be used anywhere in this well to tie seismic tying, or is that velocity data is further useful in inversion or further study reservoir studies?
Yes. It is something you can incorporate when building the low frequency initial model in order to get any kind of lateral velocity variation that you will not receive by interpolating the well logs. Nevertheless, you have most often you will see that it is not the sole input for the velocity information. Actually, most interpreters prefer to mix it up with the well-derived velocities, because your seismic-based velocities have a very, very low frequency content. Most often they don't have in terms of frequency, and that is not even enough to build a decent low-frequency model.
Okay.
So you can use it as one of the input for building the model, but I would not recommend using it for everything. And especially it will not give you the density volume that you need to do the initial impedance volume.
Okay. Thanks for now. Thank you so much.
You're welcome.
Okay, well, thank you for those questions. Now, Claire, I've actually sent you a question that somebody has recently typed in, but I'll go ahead and read it aloud for the audience. It says, is there some criteria on how final inversion models are selected when doing the stochastic inversion? As I understand, there will be a plentitude of models after the inversion.
Well, there is just one model for stochastic inversion. That's just a different realization of the well data and the data in the well, the histogram, and the spatial distribution. So I don't really get the question, I think.
Okay.
No, we cannot hear you.
Well, if the person who asked the question, if you would like to send a clarification into the questions pane, we'll be happy to send that along.
Yes. If I would add a small comment on this, you should not see the stochastic inversion realizations as an alternative to the deterministic inversion. They are not a replacement of the impedance volume you receive after a deterministic inversion, and they should never be treated individually, but always as a group. And that's why, as part of the stochastic inversion, and the one that is used to create 3D bodies is one of them. That so you get a number of utilities that can be used in order to extract and to really create geological objects out of the stochastic realizations.
The important thing about the stochastic inversion, it gives an idea of the uncertainty. So if you're So you have a, you know what is most likely or less likely. So it's important to see stochastic inversion this way.
All right, well, thank you. The person who asked the question said, okay, that explained it. So that was a perfect response for him then. Now, if anybody else has any questions, then please raise your hand or send it in. We'll give you about 30 more seconds to go ahead and do that. Additionally, if you do have questions that you come up with after the webinar, then feel free to email them in to us. You can email us at webinar@dgbes.com or just reply to any of the emails that have been sent to you. And I hope that you all will join us next month. We will be having a presentation from Arnaud, who is one of our panelists today. He will be giving a body creation webinar that will actually be incorporating the new voxel connectivity filter. So I think that should be an exciting webinar as well. So we hope you join us all next month for that. And for those of you who are new, the webinar that we have just experienced today will be recorded and posted online on Friday. So we'll send out that link in an email on Friday, and if it is posted before then we'll make a note of that on our LinkedIn page and our Facebook page, so you'll be the first to know there, and you won't have to wait until Friday to get the link. So all of our webinars are posted online. You can visit our web pages, opendetect.org or dgbes.com, and you can find your way to those. Now, if you do have any questions, we'll be happy to answer them in the future, so don't hesitate. We hope everybody had a great time today, and everybody will join us next month.